All right, in this exercise, we're going to tune a PID controller. We're going to look over 10 minutes with initially the set point at 50 degrees and then 40 degrees for the last 300 seconds. We're going to modify these tuning parameters, and we're going to use these tuning parameters of this model of our temperature control lab system, find the tuning parameters that we like, and then implement them using the temperature control lab system. So I can remember, all right, we've got a problem. There we go. I want to make sure that these are separate. So we'll just go ahead. Don't want all the code to run once one section runs. Here we go. So the idea is that these sliders change our PID parameters, then the code runs and evaluates what the integral of the absolute error would be from a model of our temperature control lab system. So we're able to interactively see and interact how the gain, how the integral gain, how the derivative control, how all of them would intuitively affect our system. You can see there, we don't really like that. How if we turn up the gain, for example, ideally it actually looks pretty good, to be honest. Now this is an ideal system, and so oscillations and other things that may be a problem otherwise aren't as much of a concern right now. So having more aggressive integral control is definitely helping us here. I say we probably want to turn the KC down a bit. Actually, let's do this. Let's look at how, it looks very good. It reaches the set point very well. Let's look at implementing this right here and see what the difference is between when we actually implement it and our simulation that we have right now. So scroll down. We're going to put in our values right here. So KC of 24, tau I of 45, and tau D, I didn't play with tau D too much. So you can see, as we turn tau D up, there's lots of oscillation within that controller. And so if we don't have a problem with oscillation, tau D is there to damp the oscillations. I'd say we keep it at 2 or let's do 3. So tau D of 3. We'll go ahead then. It's a similar loop as before. We create our arrays. We start our timer, measure, keep on going on. With our PID controller, as normal, we have error, integral of error, derivative of error. And one thing I always like checking is that the derivative, if we're taking derivative of the process variable, we need to remember right there that it needs to have a negative sign in there. So I always like checking that. We'll come here, we'll notice that the output is OPIER and the derivative. So if we come over here, we want to make sure that we have all those variables away as well. Even though we won't be doing anything with P and D, we need to make sure that the spacing's right, and then we implement the heater setting, and finally we graph it and wait. Go ahead. I don't remember what I just did this right before, but I don't know what my rationale was here. So we'll do mod of talk and 1. We'll pause for 1 minus that. And then we should be good. So let's go ahead and run this, see how well we can do. See if we can really get 36 for an integral of absolute error. Looks like we already had a connection to our TCLab, so I'm just going to push the button on my TCLab, reset it, and then we'll run it again. So we'll do lab is equal to TCLab, getting something, which tells me that what I probably want to do is lab clear lab. Then we'll try lab is equal to TCLab. See if we're able to connect. Lab, or let's just do lab.T1. See if we can get the temperature. And we can't. We can't write off. Clear lab. So clear lab on this end. I'm going to do that, and actually just to be safe, I'm going to unplug it real quick. Let's try again. And we got the error again, my word. Alright, if this is the case, I'm just going to go ahead and run the Arduino setup, try to figure out what's wrong real quick, and then we will tune our PID controller. This gives you a good idea of how we just figure things out, and it gives us a pretty good debugging process. Go ahead and program our board. Tells us what to do. First we try resetting it. That little red button is our friend. If not, we'll run Arduino setup, and if not, we have these debugging steps. Alright, there you have it. Actually what helped, I still got errors after reinstalling, but all I did was hit clear all, close all, which we kind of tend to say to do at the beginning of anything. Except we don't have on this one, so there you go. So clear all, close all, very good to do. We'll go ahead and we'll just restart now. We'll run our section. Connect it to the lab and it works. So we'll go ahead and we'll see how well we do. I'll go ahead and pause the recording and we'll see you afterward. I'm pausing really briefly. You'll notice that the IAE right here is remaining constant at a very odd 0.0075. You may wonder what's going on. Well, if you remember, we have our constraints for anti-reset windup. And so because of that, when our heater is set to 100, we're not adding anything to the integral of absolute error for our controller. So that's where we get this difference. And so the IAE, you don't see any difference while this heater's at 100. You may be wondering, you may be thinking something's wrong. But that's at least just something I thought I'd point out. All right, and here you have it. We have some more oscillation than we did within our simulations, which is to be expected, and also more shuddering if this were a valve again, mainly due to instrumentation, not error, but just our instrument can only measure, the thermistor can only measure in discrete intervals, and so we'll have these weird discrete points and bouncing back and forth between the points as it decides what temperature we're at. We don't calculate the integral absolute error within this loop, but we can do so right here. Assuming that each iteration is 1 second long, as we did before, we can just take the sum of SP1 underscore minus T1 underscore, and we get about 2,500. Obviously much more than the integral absolute error that we predicted within the simulation. I also note this doesn't have the step down, which is definitely a mistake. Nonetheless, now it's correct, and if you were to implement that, you'd have it correct. Make sure you see that line should be there. That's how you tune a PID controller. It's a little bit of trial and error. We could implement this with a higher KC. Because of this oscillation, we either want to lower the KC or lower the tau I, or increase, I should say, the tau I so there's less oscillation, or maybe we do a balance of increasing the integral importance and also increasing the derivative importance so that we hopefully counteract any increased oscillations that happen. But there you go. Hope you enjoyed the activity.